Something happened on a mountaintop in Chile that nobody in the mainstream media fully explained to you. Not because it wasn't important, because it was almost too important. On June 23, 2025, a machine opened its eye for the first time. An eye so powerful, so precise, so terrifyingly vast in its vision that in just 10 hours of looking, it found millions of galaxies, thousands of asteroids, and glimpsed light that left its source before dinosaurs walked this Earth. Scientists called it the greatest moment in the history of astronomy. But here's the question nobody is asking. What happens when we can finally see everything? There's a mountain in Chile called Cerro Pachón. It sits at an altitude of 8,900 feet, above the clouds, above the dust, above the noise of human civilization. The air up there is so dry, so still, so perfectly dark at night, that it feels almost like the universe is leaning in closer, like it wants to be seen. For decades, astronomers dreamed of building something on that mountain, not just a telescope, but a machine that would fundamentally change what it means to look at the sky. And on June 23, 2025, that machine finally opened its eye for the first time. And nothing in astronomy will ever be the same again. The Vera C. Rubin Observatory published its first telescope images on June 23, 2025, the result of more than 2 decades of planning, engineering, setbacks, and relentless scientific ambition. What the world saw in those first images was not simply beautiful, it was disorienting, because beauty you can admire and move on. But what Rubin showed the world was something that forces you to sit quietly and reconsider the scale of existence itself. Think about that for a moment. Not the scale of our planet, not our solar system, not our galaxy, the scale of existence itself. At the heart of the observatory sits the 8.4 meter Simone Survey Telescope, equipped with the largest digital camera ever built, the 3,200 megapixel LSST camera. 3,200 megapixels. Let that number land for a second. Your phone camera is probably somewhere between 12 and 50 megapixels, and you already think those photos are astonishing. Each full image snapped by Rubin's camera would require 404K high-definition television screens to display at its original size. A single image. One click of this cosmic shutter and you would need a wall of screens the size of a football field just to look at it. But here is where it gets even more extraordinary. This is not a camera designed to take beautiful pictures for posters and screensavers. This camera is a scientific instrument engineered to detect the faintest whisper of light from objects so distant, so ancient, that the photons arriving at its sensors have been traveling through the void for billions of years. It is designed to see things that human eyes, human brains, and every previous instrument we have ever built simply could not perceive. And in its very first images, it proved it could do exactly that. One of the first images released was a composite of the Lagoon Nebula and the Trifid Nebula, 2 vast clouds of interstellar gas and dust, 4,350 and 4,000 light years from Earth, respectively. These are not just pretty clouds, these are stellar nurseries. Regions of the galaxy where gravity is slowly, relentlessly pulling gas and dust together until the pressure becomes so enormous that hydrogen atoms begin fusing, and a star is born. Every star you have ever seen in the night sky was once a swirling pocket of gas inside a cloud just like this one. The Lagoon and Trifid Nebula image is a composite of 678 individual images assembled from roughly 2 trillion pixels of data, taken across more than 7 hours of observation. And yet, in the final image, you're not looking at a blurry smear or a vague glow. You are looking at intricate filaments of dust, glowing wisps of ionized gas, the delicate structural anatomy of star formation, all of it sharp, all of it detailed, all of it alive with information that astronomers have never had access to at this scale and resolution simultaneously. But that was just the opening act. The Virgo cluster lies some 65 million light years away from Earth, and it is home to more than 2,000 galaxies, scattered across a region of space spanning tens of millions of light years, 65 million light years. The light in Rubin's images of the Virgo cluster left those galaxies when the most complex life on Earth was a small, furry mammal sorting out how to survive in a world still recovering from the extinction of the dinosaurs. That light has been traveling through empty space for 65 million years, and it arrived at a Chilean mountaintop and was caught precisely by a 3,200 megapixel camera built by human hands. Think about what that means. We built a machine to catch 65 million year old light, and it worked. In Rubin's wide view of the Virgo cluster, except for a handful of foreground stars in our own Milky Way, every single point of light in that enormous image is a galaxy. Approximately 10 million galaxies in total. 10 million galaxies. In one image, from one night of observation. Each of those galaxies contains hundreds of billions of stars. Each of those stars may have planets. And Rubin's 10-year mission will capture approximately 20 billion galaxies before it is finished. Those 10 million galaxies visible in the first wide-field video are roughly 0.05% of the approximately 20 billion galaxies Rubin will ultimately capture. Not 5%, not half a percent, 0.05%. This is what scientific humility actually looks like. Rubin hasn't even started yet, and it's already shown us more than we could process. Now here is where the story stops being about beautiful images and starts being about something far more unsettling. What Rubin is actually built to find is not the things we already know are there. It is built to find the things we know exist, but have never been able to see directly. It is built to hunt the invisible architecture of the universe. We know that approximately 27% of the universe is made of something called dark matter. It does not emit light. It does not reflect light. It does not interact with light in any way we can directly detect. And yet it is there. We know it is there because of a woman named Vera Rubin, the same astronomer this observatory is named after, who spent decades in the 1970s and 1980s studying how galaxies rotate. What she found was a problem so serious, it shook the foundations of physics. The observatory is named after astronomer Vera Rubin, who provided the first convincing evidence for the existence of dark matter. What she discovered was that stars at the outer edges of galaxies were orbiting far too fast. According to the laws of gravity, the stars at the outer edges should be moving slowly, like the outer planets of a solar system. Instead, they were moving almost as fast as the stars near the center. The only explanation that worked was that there was a massive invisible halo of matter surrounding every galaxy. Matter we couldn't see, matter we couldn't touch, matter that nevertheless had gravitational weight. She called it dark matter. The scientific community initially pushed back. They doubted her. They questioned her methods, her data, her conclusions. She kept going. She was right. And now the observatory that carries her name has been built specifically to finally understand what she discovered. That is not a coincidence. That is a mission. The 4 primary science goals of the Rubin Observatory are probing dark energy and dark matter, mapping the Milky Way in unprecedented detail, taking a comprehensive inventory of the solar system, and exploring the transient optical sky, the universe of objects and events that change over time. Each of these 4 goals, taken individually, would be enough to justify building the most powerful survey telescope in human history. Together, they represent the most ambitious scientific program ever attempted with a single instrument. And what makes Rubin uniquely capable of all 4 simultaneously is something that no previous telescope has managed to achieve. It is both wide and deep, both fast and sensitive, both a cataloger of the known and a hunter of the unknown. Let's talk about what it found in just the first few weeks of looking. In just over 10 hours of test observations, Rubin had already captured millions of galaxies and Milky Way stars and thousands of asteroids. Thousands of asteroids in 10 hours. Not discovered over years. Not compiled from decades of survey data from multiple telescopes around the world. 10 hours. But it gets more specific than that, and the specifics are what make your stomach drop. In just a month and a half, during early optimization surveys, Rubin discovered over 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects. Near-Earth objects are exactly what they sound like. Asteroids whose orbits bring them close to Earth. 33 of them discovered in 6 weeks that nobody knew existed before Rubin opened its eye. These are not academic discoveries. These are objects moving through the neighborhood of our planet in orbits that cross or approach Earth's own path around the sun, and we didn't know they were there. This is not a cause for panic, but it is a cause for serious, clear-eyed reflection on what our previous level of knowledge actually was. For decades, we believed we had a reasonably good catalog of near-Earth objects above a certain size. We believed that with our existing telescopes and survey programs, we had found most of the significant threats. Rubin revealed, in its very first weeks of operation, that 33 of these objects had simply been invisible to us. Not because they were hiding, because our instruments were not good enough to see them. Now imagine what it will find over 10 years. In the first peer-reviewed scientific paper to use data from the LSST camera, astronomers announced the discovery of the fastest ever spinning asteroid with a diameter over half a kilometer. An asteroid nearly the size of 8 football fields, rotating every 2 minutes. For context, the Earth takes 24 hours to complete a rotation. This asteroid, half a kilometer wide and spinning at a rate that would tear apart any loose pile of rubble, is held together by something, its own internal cohesion, its composition, its structure. And understanding why it can spin that fast tells astronomers something fundamental about how asteroids form, how they evolve, and what they are made of. That knowledge matters when you are eventually thinking about how to deal with one that might be coming toward you. But Rubin is not just watching the solar system. It is watching the entire universe change in real time. This is the dimension of its mission that is hardest to wrap your mind around, because we tend to think of the universe as static, as a backdrop, as scenery. In reality, the universe is in constant motion, constant transformation, constant upheaval. Stars explode. Black holes devour matter and flare with radiation. Two neutron stars collide and release more energy in a fraction of a second than our sun will produce in its entire lifetime. Galaxies merge and tear each other apart across timescales of millions of years. All of this is happening right now in every direction you can point a telescope. The universe is not a still photograph. It is a movie, and Rubin was built to film it. Each night, Rubin collects approximately 10 terabytes of data and produces as many as 7 million alerts of changes in the night sky. 7 million alerts every night. Every single morning, a river of 10 terabytes of raw cosmic data flows down from the mountaintop in Chile and into a network of supercomputers that begin processing it in real time. Algorithms scan every image, comparing it to previous observations of the same patch of sky, by flagging anything that has changed. A star that has brightened, a galaxy that has flickered, a point of light that has appeared where there was none before. Those 7 million nightly alerts are then distributed to astronomers around the world, who can follow up with other telescopes, point other instruments at the most interesting events, and begin untangling what is happening. It is not just one observatory looking at the sky. It is Rubin as the conductor, and every other telescope on Earth as the orchestra. The color-rich images of exploding stars, black holes, and cosmic collisions will also help direct the attention of other observatories around the world, allowing various institutions to work in tandem to collect comprehensive observations of notable celestial events. This is a paradigm shift in how astronomy is actually done. Previously, discovering a supernova, a star that has exploded, often meant that by the time anyone knew about it and pointed another telescope at it, the most dramatic phase of the explosion had already passed. With Rubin's nightly all-sky coverage, the discovery happens within hours. The alert goes out. Telescopes around the world slew to the coordinates. The event is captured from its earliest moments through its evolution and eventual fading. The science that comes from that kind of comprehensive, time-resolved observation is exponentially richer than what we had before. In the first images already, the rich detail is proving illuminating. Hues of blue are coming from relatively nearby galaxies, while red tints emanate from remarkably distant and primeval galaxies. And in the images of the Virgo cluster, plumes of diffuse light erupting from several galaxies reveal halos and illuminated bridges between them, records of these ancient galaxies' ancient pasts. These bridges of stolen starlight between merging galaxies are the fossils of gravitational catastrophe. They are the aftermath of collisions that happened hundreds of millions of years ago, and they are still glowing, still stretched across the void, still telling the story of what happened long before any complex life existed on Earth. And Rubin can see them, all of them, across the entire southern sky every few nights, forever. The word forever is not quite right, of course. The new $473 million Vera C. Rubin Observatory will conduct a 10-year time-lapse of the sky, comprising 2 million images and 30 trillion measurements of the properties of billions of galaxies, stars, and asteroids. 30 trillion measurements. In a decade. That is a number so large it is almost meaningless to say out loud, but what it represents is this: the most complete, the most detailed, the most comprehensive map of the observable universe that humanity has ever attempted. By the time Rubin's legacy survey of space and time is complete, we will know more about the structure of the cosmos, its history, its contents, its hidden forces, than the sum total of everything learned in all of recorded human astronomical history before it. That is not hyperbole. That is the actual scientific assessment of what this instrument is expected to deliver. But there is something that does not make it into the official press releases. Something that sits quietly beneath all the celebration and the stunning images and the budget justifications. Something that scientists acknowledge but rarely dwell on publicly, because it lives in the uncomfortable territory between scientific ambition and genuine uncertainty. And it is this: Rubin will almost certainly discover things we are not prepared to explain. This is not alarmism. This is the honest prediction of every major telescope ever built. The Hubble Space Telescope was built to measure the expansion rate of the universe with precision. It succeeded, but it also discovered that the expansion rate we measured conflicts with the expansion rate measured other ways. A discrepancy now known as the Hubble tension, one of the most significant unsolved problems in cosmology. We did not expect to find a problem. We found one anyway. This is what powerful instruments do. They reveal the gaps in our understanding. Rubin, with its unprecedented depth and breadth, scanning the entire southern sky every few nights for a decade, is almost guaranteed to find things that do not fit. Objects that should not behave the way they do. Patterns in the large-scale structure of the universe that do not match our models. Transient events that occur in ways we have no framework to explain. And when that happens, and it will happen, the work of astronomy does not end. It deepens. It gets harder and more interesting and more necessary. because every unexplained observation is not a failure. It is a door. The woman this observatory is named for understood that better than almost anyone. Vera Rubin spent years presenting data that the scientific establishment did not want to believe. Her evidence for dark matter was rigorous, methodical, and reproducible. And she was still met with skepticism, dismissal, and the quiet condescension that women in science faced in the 1970s as a matter of routine. She never received the Nobel Prize, despite the fact that her discovery of dark matter is arguably among the most consequential contributions to physics in the 20th century. She died in 2016, 9 years before the observatory that carries her name opened its eye for the first time. She did not live to see this moment, but everything this machine is doing, every galaxy it counts, every asteroid it tracks, every wisp of dark matter it traces through the distortion of distant light, it is doing in the tradition she established. The tradition of looking harder, longer, and more carefully than anyone else, and refusing to discard what you find simply because it makes the universe more complicated and more strange. As the observatory officially began its 10-year survey mission, the team declared, "Today, we begin filming the greatest cosmic movie ever made." That language is deliberate. Rubin does not take snapshots. It films. It captures change. It is not an archive of how the universe looks right now. It is a living record of how the universe moves, evolves, flares, fades, collides, and transforms across time. The Legacy Survey of Space and Time is named exactly for what it is: a survey of how space and time behave together, written in the language of photons across a decade of unbroken observation. Rubin will also advance opportunities for multi-messenger astronomy, the study of cosmic events using multiple signals such as light, gravitational waves, and cosmic rays. We detected gravitational waves for the first time in 2015. When two black holes merge, they send ripples through the fabric of space-time itself, ripples that can be detected here on Earth as infinitesimal stretches and compressions of the distance between objects. When two neutron stars merge, they produce both gravitational waves and a burst of electromagnetic radiation across the entire spectrum. And in 2017, we caught one in the act, seeing both the gravitational wave signal and the light simultaneously for the first time. But events like that are rare, fleeting, and distributed across billions of light years. You have to be looking in the right place at the right time. With Rubin watching the entire southern sky every few nights, the odds of catching these events, and catching them early enough for other telescopes to join in, increase dramatically. We are entering an era of cosmic surveillance that no previous generation of scientists could have imagined. Dedicated computer facilities will process Rubin's data in real time and issue worldwide alerts within minutes of detected changes in the sky, creating a treasure trove of discoveries about asteroids and comets, supernova explosions, and more within minutes. The universe changes, Rubin sees it, the computers process it, and astronomers on 6 continents are alerted, all within minutes. This is not how astronomy used to work. Astronomy used to be a slow, patient, solitary pursuit. You applied for telescope time months in advance. You waited for the right alignment of weather and schedule. You gathered your data. You analyzed it over months or years. You submitted it to a journal. You waited for peer review. And then, if you were lucky, the community learned what you had found. That pipeline still exists, and it should. But layered on top of it is now something entirely new. A real-time global alert network for cosmic events, powered by the most capable survey instrument ever built, running every clear night for the next decade. What will it find? That is the question that keeps astronomers awake at night. Not with dread, but with the particular sleeplessness of people who are standing at the edge of something enormous and can feel the ground changing beneath their feet. The conservative answer is that Rubin will find more of what we already know. More asteroids, more supernovae, more merging galaxies, more dark matter traces, more evidence about the nature of dark energy. And the conservative answer is probably correct, as far as it goes. The discoveries within the known categories will be staggering in their volume and their detail. But the history of astronomy suggests that the most important discoveries Rubin makes will not fall neatly into any existing category. The history of astronomy is a history of finding exactly what you were not looking for. Pulsars were found accidentally by a graduate student who noticed a strange, impossibly regular pulse in radio data, and initially wondered if it might be a signal from an alien civilization. Quasars were thought to be nearby, faint stars, until their redshifts were measured and revealed them to be the most luminous objects in the universe, powered by supermassive black holes consuming matter in the earliest galaxies. Dark energy itself was a complete shock. Astronomers measuring the expansion rate of the universe expected to confirm that gravity was slowing it down, and instead discovered that it was speeding up. Nobody predicted that. Nobody had a framework for it before it was found. And yet, there it was, written in the light of distant supernovae, undeniable and unexplained. Rubin will look at more of the sky, more deeply, more often, and with higher fidelity than any instrument that has come before it. The probability that it will stumble onto something that breaks an existing model is not small. It is essentially certain over a decade of operation. The only question is what it will be. And that question, that genuine, wide-open, nobody knows the answer question, is perhaps the most exciting thing about this moment in science. Because right now, on a mountaintop in Chile, above the clouds, under the darkest and stillest skies on the surface of this planet, a machine is watching. Every clear night, it opens its eye. Every 40 seconds, across a field of view equivalent to 45 full moons, spread side by side across the sky, it captures a new image. Every morning, 10 terabytes of data flow down from the mountain and into the computers. Every night, 7 million alerts go out to the world. And somewhere in that river of data, in the light of some galaxy, in the orbit of some asteroid, in the flicker of some dying star, in the subtle distortion of some background galaxy's shape bent by invisible mass, somewhere in all of that is something we have never seen before. Something that will force us to rewrite a chapter of physics, or astronomy, or our understanding of what the universe is made of and why it behaves the way it does. We just do not know yet what it is. That is not a limitation. That is the whole point. Science is not the process of confirming what we already believe. It is the process of going somewhere we have never been, looking at something we have never seen, and then being honest about what we find. Even when what we find is uncomfortable, inconvenient, or impossible to explain with the tools we currently have. Vera Rubin did exactly that for decades, in the face of institutional resistance, with nothing more powerful than a spectrograph and an unwillingness to discard data that told the truth. The observatory that carries her name has been built in that same spirit. It is not just a telescope. It is a commitment to looking harder, to seeing more, to following the evidence wherever it goes, no matter how far from the familiar it takes us. The universe has been up there the whole time, patient, vast, largely invisible to us. And now, for the first time, we have an instrument worthy of its scale. What it shows us next is a question without an answer, and that is exactly where science lives.